Hello again. So in this video, we're going to continue talking about loops in MATLAB. In particular, we're going to talk about another variant of a loop in MATLAB, which is a for loop. And we are going to look at using while loop to compute approximations. And lastly, we're going to talk about nesting of different loops here. So let's jump in and start with the code we wrote from last time. So if you remember, we declared a loop variable and then a couple more variables to limit how many times we're going to run, and then sum to hold a cumulative summation. And we wrote the while loop with condition, something we want to repeat, increment, and at the end we simply displayed the result. So let's take a look at what that looked like. Right, so we get the sum of 55. And what we're going to try to do now is translate this code with the same functionality to be a for loop. So keep in mind the procedure I just illustrated here of how we wrote this while loop. And we're going to do the same procedure for the for loop, but because for loop is kind of the special version of a loop, the procedure for it is going to be a little different. So first of all, there is no loop variable. So we're going to jump right into writing the loop itself. So we start with keyword for, and here, instead of giving it a condition, we're going to give it an assignment. And again, we're going to look at what that looks like in a bit. And we are going to put something we want to repeat. And that's actually about it. So you can see right off the bat that for loop is probably going to be more compact than the while loop, and that's exactly what it is. The functionality, there is nothing that's too much different from the while loop. We still get to repeat what we want to repeat, but instead of checking condition every time, we are going to use an assignment to declare how many times we want to repeat things. So let's see what that looks like here. And I said just a minute ago that we do not need to use a loop variable here. And that is because this assignment generally is what the loop variable is going to be. So in order to go from 1 to 10, instead of starting from 1 and manually incrementing it until it reaches 10 here, we are going to just simply give it values from 1 through 10. So this now is a row vector, right, of 1 all the way to 10. And what we want to do is, again, we would need a sum that starts from 0, and simply sum is going to be taking the existing sum and adding the new term. All right, so let's display this. So since we're displaying the sum twice, we can expect this to be repeated twice with the same number, given that we've written the loop correctly, and let's see if that is the case. Okay, so that worked. And because the syntax is a little more compact, you might be a little confused on how this worked out. So unlike the while loop, where we increment and reassign I ourselves, this deal of having to assign some value to I is taken care of by MATLAB when we use a for loop. So what happens when this loop runs? So first we start with sum equals 0. Okay, that's standard. And then when it first hits this line, right? So let me write this more explicitly so that we can see what's going on. The first time this line of assignment runs, the I is going to be assigned a value of 1. And then it goes into the body of the loop and computes the sum. And then it loops back. And then it assigns the value of 2. Let's mark this as used. And then I is 2, so we get 1 plus 2 equals 3 as sum. And then loops again. And then 3 is assigned as the value of I. And with the existing sum, we get 3 added, so we get 6, and so on and so forth, until all the members of this row vector is exhausted completely, and then the loop terminates. And that is how for loop works. So again, just to highlight the differences here, the key element, which is common in both loops, is something we want to repeat. As you can see, the syntax is exactly the same. However, reassigning and incrementing or changing the loop variable is taken care of by MATLAB when we use for loop. So we don't have to increment it because the assignment changes every time this line, so line 29, runs. So that is the basics of for loop. And now we are going to look at how to do approximations. And for that, we're going to just jump quickly back to while loops for a bit. So the example we looked at in class was approximating a value of sine. And let's say we want to do exactly that and approximate value of sine 45 in degrees, of course. Okay, so we are going to be writing a while loop for this, and I think this is a good place to kind of highlight the difference between a while and a for loop. Other than the differences we saw in application, while loop does not require knowledge of how many times we need to run. And this will be pretty clear once we write the loop for the approximation. However, because for loop requires assignment of values, right? We can't assign infinite values to a variable. We must know how many times loop will run. So those are two differences. And because when we're approximating a value by continuing the summation process, we don't know at what point we can stop, and we don't know at what point we will achieve the accuracy we're going to achieve. So that's why we are going to be using a while loop here. So let's do some setup, and let's set degree as 45, and let's set x, which is going to be our radian value, to be the degree value times pi over 180 so that we can do the conversion. And just like those simple examples of summing 1 to 10, we are still doing the summation. So let's set sum equal to 0, and we are going to set the loop variable. In our case, let's use n here, and we're going to set that to 0. And we're using n just because that's what the formula has. And the formula for approximating sine goes something like this. So I'm just going to write it in code here. 2n plus 1 divided by factorial of 2 times n plus 1, okay, times, all right. So the approximation of sine, you can say, is this. So let's say sine x is approximately that, and just make that a comment since that's not actual MATLAB syntax there. And we're going to use this formula to approximate. And what this gives us is a one term of the summation. So actually, in order to approximate this, we need a summation from 0 to n, and n, let's not do n, m, depending on how many terms we want. This will give us approximation. Okay. So now jumping in, we did a setup. We declared the loop variable n because n is something that needs to be changed for every term in the summation. So we're going to write the loop now. So while some condition, we don't know yet, and say what we want, to repeat and increment, of course, and then end. All right, so let's figure out first what we want to repeat here. Again, we're doing the summation, so it makes sense to start doing sum equals take the existing sum, and we need to add something to it. And we are going to continue doing that until we have the accuracy we want. So in order to express that, we are going to simply do, okay, so if we write that in English, it will be while we have error that is larger than desired epsilon, right? So if we write that in code, maybe something like this would work. Error larger than, let's say the epsilon we want is 0.00001. Okay, and we can use that directly as the condition here. So let's write that here, while error is greater than 0. That. Okay, and notice that we don't have this error variable, so we must have it. And let's just give it some arbitrarily large number, because with just the first term, or without any term, the error is going to be very large. And it doesn't really matter what the first value, initial value of error is, because that will be changed quite soon when the loop runs. Okay, so now for this term, remember when we did the summation from 1 to 10, the I was the term. And if you think about what the summation formula looks like on paper for your math for summing 1 through 10, literally I was what the term was. And the same concept applies, and anything that comes from the single term of a summation formula can be used right here, because that's what we're doing. We're computing a new term in the summation. We're adding it to the existing sum, and that's our next value for the sum. So now that we have this, the only thing that is left here is an increment. Okay, so sure. So now because we had loop variable n, we can maybe do something like n equals n plus 1. And okay, that makes sense. We start with n equals 0, and then following from formula, we are supposed to plug in 0 at first to this formula, and then 1, and then 2. But what is missing right now? Can you see? If you saw something that is missing, hold on to that thought. But if not, let's just run this and see what happens. It looks like we got all our pieces, but this loop is running seemingly forever, and meaning we did something wrong, and this condition is not changing, right? Whenever we get a infinite loop, the reason is because this condition is always going to be true. Okay, so let's investigate why that might be. And it's not too difficult to see, because we realize that we assigned the value 1000 to the variable error, and we are not changing it, right? So remember, even though you're incrementing this loop variable here, if we're not doing anything to change this variable that is part of the condition, then this condition will stay the same forever. So what we need to do here in order to match the logic that we are following, we must recompute the error, correct? And in order to do that, we have to do a few things. And here, for the convenience sake, we are going to say that error in reality is just a previous sum minus the current sum absolute value. Okay, so all right, so we have the current sum here, but we are not keeping track of what sum was beforehand, so it looks like we need to do that. And it's pretty simple, right? So before this line runs, the sum is not updated yet, so maybe we'll just save that value as prev sum here. And to calculate the error, we'll just follow the formula to get absolute value of prev sum minus this sum, which was just updated to be current. And let's see if this would work. Okay, so it finished. So let's see what that value became. Let's display sum here. And run it again. All right, so I think that's about good value that we wanted to get. So that is how we do the approximation. So again, if you wanted to look at how this worked and how things are changing, you can get rid of the semicolons for just this instance and take a look at how the values are changing. Okay, so we can see the previous sum was 0, and then we got the new sum, and the n is 1. That's the number we will be plugging in next iteration right, to this formula. And then our error got updated. Okay, so it's definitely bigger than our epsilon that we gave. So it continues on until it sees error that's really, really tiny, enough to make this condition false, and at which point we should have pretty good approximation. Okay, again, just like last time, I encourage you to all write this yourself without any help to see if you can do something like approximation for different sine value, for example, or cosine value, whatever that may be, right? Okay, so that was the approximations, and now we're going to quickly talk about nesting of loops. So remember, the loops are nothing special except a tool that lets us repeat whatever we want, right? And sometimes whatever we want is repeating some other things. So just let's look at a quick silly example here. I'm going to use a for loop. So for I equals, let's do 1 through 3. And what I'm going to do is I'm just going to display it. And let's use disp to make it more compact. And let's say this right here is something I want to repeat. All right, so printed 1, 2, 3. But what if I wanted to print 1, 2, 3 5 times, right? Then this whole loop becomes something I want to repeat, right? So let's write that. This whole loop of printing or displaying 1, 2, 3 is what I want to repeat. Then what I can do is write another loop around it. Say, let's use for loop again, and give it a different variable so that we don't mess with this. And this time I'm gonna assign 5 different things so that it runs 5 times, and see what happens here. All right. Okay, so now you can see, oh, so what I wanted to repeat was printing 1, 2, 3, so it just repeated that 5 times. So this is the basics of nesting, right? Again, silly example, seemingly useless. But let's go back to our real example here and see how we can apply that. So here we only computed the single sine value of 45 degrees, but what if we wanted to compute a whole bunch of them? So say from 0 all the way to 360 to get the whole range of sine values, right? Then we are going to repeat this approximation 360 times. So this whole loop becomes something we want to repeat. All right. Then, like I did on the silly example, I'm going to write another loop around it, and again, use a for loop. So for, and take a look at what is being used here for the formula, right? We're using x. Okay, so it looks like the x needs to be part of the setup before we can run the loop. So I'm going to paste that in here, right? Because we want to setting up or converting from degree value to radian value to run every time for every degree value we're going to be computing, right? And okay, yeah, the approximation needs to start from 0, right? This approximation, so that's also part of the setup. Okay, how about n? Yeah, n also needs to start from 0 for every approximation, for every angle value we have. And same with the error. So that error can be reset to be something large to let this while loop run to begin with. Okay. So what we ended up doing is getting all the setup stuff, right, including the loop variable and our degree or degree to radian conversion, and resetting some to 0 and error to 1000, all in here. So this whole expression became something we want to repeat. And if it didn't make much sense why we moved this from outside of the for loop to the inside, realize what's going to happen when we run this, just this while loop multiple times. Okay, so let me complete the for loop first and say that, okay, so for our D value, which is going to be this, right? So we can use this assignment directly. 0 to 360 degrees. We are going to repeat this. Now, let's say we didn't have all this. Say we were missing these three. Then, okay, so for loop is going to start with the D as 0. So it's going to get converted to radians. And then the approximation is going to run. Let's say that these are outside, out here, like so. Okay, so for the first iteration, this should be fine. Sum is 0, so we're going to start adding things from 0 in the next term and the next term. And n, we are going to plug in 0, 1, 2, 3, and so on. And error is going to start off at 1,000, so this is going to run, and then new error is going to get computed. Okay, so that's good. Everything went fine for degree value that was equal to 0. But once this thing computes and finishes, we are still going to retain that value, whatever sum we got for the degree equals 0, and the n equals 0, equals whatever number up to we went up to, and then really small error, which caused this loop to terminate, or this condition to be false. And then we're going to attempt to evaluate this again, which will be false, and nothing else will be run. So maybe we'll just run it to find out what happens here. Okay, well, we're missing all the displays, so let's display the sum here to see what happens. And all right, so it looks like we got just zeros and nothing else, meaning, yeah, this for loop ran for 360 times, but we only got 0 as the answer for the sum, because this while loop run once inside the for loop, and then every subsequent time it was false. This condition was false, so it didn't run. Sum was same, so we just ended up getting 0 360 times. Okay, so let's fix this and put the setup back in here. Redent and see what happens if we run now. Okay, so it looks like we got values that are decently oscillating, and that looks good to me. So this is an example of how we can use nesting to deal with multiple values. And note that this doesn't have to be a colon operator here. We can put whatever values we want, 14, 15, 30, 45, 180, right? And run this, yeah, to get the approximations. And we can, of course, make the approximation a lot more accurate, like so, by changing this tolerance or error value or epsilon value. So this will be really useful for engineering applications where we do need to use the approximation and we do need to write the loop ourselves to compute it. So I think that covers about everything I wanted to cover. So I will see you next time.